So thanks very much to Christoph. Next speaker is Benjamin Hesse from the Technical University of Munich in Germany.
So, good morning everybody. I will today talk about reduced reverse water flow in tree roots, and all of this in the context of hydraulic redistribution. So I want to start with something we all have to face, and it's a challenge we all know about. It's climate change. We know that there will generally be probably an increase in the mean of the temperature, so it will get warmer and all over the planet. But there also will be an increase of extreme conditions such as storms, drought periods, or for example heavy rainfall. And for Central Europe, especially for the forest ecosystems, there's maybe one solution to that, and that could be, for example, mixed species forests. As some studies have shown, they are more stable, they are more productive. As you see here in this scheme, on the left side, for example, it would be that all of this is from species 1, and on the right side it would be that all of the trees are from species 2. And if you go to the middle, you see that the shape is going up, so that actually we are more productive and more stable. And the reason behind this could be facilitative effects, such as hydraulic redistribution. So, a short introduction to what is hydraulic redistribution. Easily said, it's the redistribution of water from very dry soil layers from moist soil layers to dry soil layers via the plant roots. As you can see here, for example, in the sketch number B, which is called hydraulic lift. So this would mean, for example, that deep rooting trees could take up like groundwater or water from still moist soil layers and redistribute it to the shallow, drier soil layers. From this redistributed water, neighboring trees could maybe make use, and by that be supported by the neighbors. So far, this effect has mostly been found in arid and semi-arid areas, so like savannas or deserts. But we also have now first findings in Central Europe. But we also found in our first studies that HR seems to be a bit species dependent, so not every species does it in the same amount or even at all. So for our experimental setup, we used the so-called split root system approach. As you can see on the sketch on the right, we have two pots. The one pot is moist, so it's well watered, and the pot on the right side is a dry pot, so it's just drought stressed. And we actually have 3 trees in it. So the one in the moist pot is of course just for control. The one in the right pot is drought stressed, and the tree in the middle, the root system is actually split. So half it is in the moist side and the other one is in the dry side. And this plant can actually redistribute the water from the moist side to the dry side. We use 6 European tree species, 2 conifers, 2 diffuse porous angiosperms, and 2 ring porous angiosperms, to also have a broader range of anatomy. And in the first experimental results, we saw that for the dry plant you saw in the right pot, the water in it was about 60% of HR water. So 60% of the water in this plant was actually redistributed water. So we can see, at least under experimental conditions, this effect seems to be very significant, or at least seems to have an influence. And our next step, of course, is now take this all to the field, so to the forest. As you see on the right, we have a nice field site next to Munich, and we want to see what is the relevance of this effect actually in the forest. But today I want to talk about something else, so not the field. We thought about, okay, we see that this effect is occurring, but now we want to know what are defining factors. So what are the limitations behind it, and what are just defining the amount of redistributed water. So one could be, for example, the water potential gradient between the moist soil layers and the dry soil layers. Another one, for example, could be mycorrhizal bridges. As we've seen, some studies shown that the trees can actually exchange nutrients and also water. So maybe this is one part in this. Then we thought also it can be that this redistribution is not over the mycorrhiza, but also over the soil. So maybe the root contact or the distance between roots from neighboring trees may play an important role in this effect. And then the last we thought about was actually the root anatomy or the conductivity of the roots, because they cannot distribute more water than they actually can conduct. And this is also where my part in this big experiment was. So I was doing the root anatomy and conductivity stuff. And I was generally facing 2 questions or 2 hypotheses. The first one was that we want to have a look at the very, very fine roots and the, well, we call it secondary roots, so the bigger roots. And we wanted to relate their anatomy to each other and to the stem anatomy. And the second question was, as during HR, water has to be transported in the reverse direction, so from the stem to the root tip. We wanted to see, is there a difference between the forward and the reverse flow in roots? So for the first question, we didn't use the classical approach in cross-sectioning, we would use laser ablated cross-sections. So our roots were actually cut by a laser and then high-quality images were taken. And we did that for, so far, 2 kinds of roots. So the primary roots, the very fine ones, which are diameter of 0.2 millimeters, and for a bit bigger roots with about diameter of 1.5 millimeters. We measured a whole lot of parameters, but today I want to show you the most interesting one, or the most, well, the easiest ones, let's say. It's the conduit diameter and the vessel density. Here, for example, some pictures of these laser ablated cross sections. I wanted to put them in here, not just only because they look very nice, but also just to see what we worked with. So you can see all our 6 species, and in the top row you can see our secondary roots, and in the column below and the row below you see our primary roots. So for our first result, for the conduit diameter, the white box plots here are for the primary, so the very fine roots, and the gray box plots are for the bit bigger roots. As you can see, the very fine roots, they are more or less very similar among all species, no matter if it's a conifer or if it's a ring porous species. At least statistically there's no difference. We see that there are obviously some small differences, but they are not as big as you see them, for example, in stems. If you focus now on the gray box plots, you can see that there are, of course, clear differences. You see that the conifers, they don't really change their size of their conduits at all. And while the ring porous species have the biggest vessels in the end. But something interesting we found, for example, if you now focus on the picture on the right bottom, we see that the ring porous species, or better I should say the stem ring porous species, they show diffuse porous roots. So they don't really show the typical stem, typical ring porous architecture. As you can see, the vessels are clearly distributed all over the place. For the vessel density, it was quite astonishing to see that in the very, very fine roots, about half of the complete vessel, root cross-section is sometimes occupied by vessel lumen, so by conductive elements. And we saw that for all 4 our angiosperms, so from maple to oak, no matter if they're diffuse porous or ring porous. And we saw then again for the bit bigger roots, the vessel density is very reduced, so it's close to the vessel density of stems. So now to the, for me at least, more interesting part, the conductivity of roots. We used the xylem embolism meter for our measurements, and we took roots after the first branching, as you can see here indicated by the red box. And we took 2 consecutive pieces. So first we took 1 big piece and then we cut it into 2 pieces. And one of these pieces was measured in the forward direction and the other one in the reverse direction. We did that to avoid some extra bias. If you would have taken 2 roots, maybe they were of different age, maybe they were different developmental stage, so we wanted to take them as close together as possible. And our mean root diameter for our measurements here was about 2.4 millimeters, so more or less close to our secondary roots in our anatomy studies. If we now first focus on the conifers, you see again here on the left, so the white box plots are for the forward flow, so the normal flow direction from the root tip to the stem, and the gray box plots would be the reverse direction. We actually see there's no big difference. They in general have very low conductivity, which is not very surprising for conifers. But if we now go to all of our angiosperms, we see that for all of them the gray box plots are smaller or lower than the white box plots, and we actually saw that there's a reduction of 30% in the reverse flow compared to the forward flow. So this was first of all to us a bit of a surprise, because most people assume the xylem as a pipe, so why should there be a difference in one direction to the other? So we then thought, okay, why is there a reduction? And we saw, okay, it was only in angiosperms. And if you look at cross sections of conifers and angiosperms, the first difference that occurs to everyone, the angiosperms have vessels. And so we thought maybe all of this is just related to the vessel architecture. We then also went a step further because we wanted to see, okay, we found this now in roots. So we also measured in the stem of our little trees. And surprisingly, we didn't find any differences in the forward or reverse flow. So this reduction occurs so far only in the roots and not in stems. So we came up with four ideas that might be related to that. It's much speculation behind that. The first would be, for example, we have elements that are pointing into our vessel lumen. If these would, for example, now be asymmetric, this would mean that one direction could have a smoother flow than the other one, and the turbulent flow could cause a reduction in the conductivity. Another thing is that in some first sections we saw that the pit aperture openings are sometimes very asymmetric. And if this is generally the case, this could also mean a reduction in the flow. Then vessel tapering or narrowing is something that has already been reported for stems, but only in a very small range. But if we now think back to the root system I showed you before, that showed that more or less within 30 centimeters, the root diameter decreases from 1 centimeter to 0.1 millimeter. So maybe this narrowing is just very much, has a higher significance within the roots. And the last idea was maybe the perforation plates between, or the connection point between vessels are just also somehow asymmetric or have some extra stuff on one side, so they could also maybe reduce the conductivity. These are just four very hypothetical ideas. We want to test them now in the next step. We want to take SEM pictures of our vessel insides and of pits to somehow see if we can maybe get some clues on the ideas we have so far, or if we find something new in it. And the other step we want to do is, as you remember the slide from the beginning, we want to connect now the conductivity to the amount of redistributed water. So we want to put it all in one big context and see how much is the conductivity dependent on the redistributed amount of water. So just to come to the conclusion of the data I showed you today, for the cross sections we saw that in primary roots for several anatomical parameters there is no big difference between species, so they are quite similar among all species, while secondary roots or bit bigger roots show already huge differences. But to mention this again, stem ring porous species tend to have diffuse porous fine roots. And for our second part, we actually saw that there's a reduction of 30% in the reverse direction. We saw this only in angiosperms, not in conifers, so we assume this is all related to the vessel architecture. And with that, I'm already at the end, and I want to thank you for your attention.